This is Pre-Calculus B, Unit 2, Lesson 8, Inverse Trigonometric Functions. We need to define what an inverse function is. So this is review. We've worked with inverse functions before. Inverse functions. The inherent idea, or the basic idea of inverse functions, is the idea of undoing. If you take a number and add 3, then the inverse of that is to take away 3. And we end up right back where we started. If we take a number and multiply 4, then the inverse of that is to divide 4, and we end up back where we started. So the official definition of an inverse function is g and f are inverse functions if g composed of f equals f composed of g, meaning it doesn't matter what order you compose them in, equals x, meaning that it takes you back where you started. That would be the definition of an inverse function. We find inverse functions, if you recall, y equals 2x minus 5, by switching the variables, switching the x and the y. So x becomes 2y minus 5, add 5, x plus 5 equals 2y, divide 2, y equals x plus 5, divide 2. Okay, so this inverting or switching of variables. So x and y change. So if I have the point 4, 1, then the inverse of the point 4, 1 is the point 1, 4. Because the x and the y are switched. If I have the point 2, 1, then the inverse of 2, 1 is the point 1, 2. Okay, and there's this symmetry that goes on in the graph. So all this symmetry that happens here. If we graph the line y equals x, which is a nice diagonal line, there's kind of symmetry going on. There's this matching points perpendicular from each other right across that line. They are reflected across the line. Okay, so let's go to Desmos and play with it a little bit there. Get rid of our previous video stuff here. So let's say I've got a table here, okay, of values. So 1, 2, 3, 4, 6, 8, 7, 5. Okay, and if I graph that, then the inverse of that would be to switch the x and the y. Okay, and let's graph that standard here. Okay, the inverse of that would be look something like this. Switch the x and the y, we get 6, 8, 7, 5, 1, 2, whoops. We do have the cursor in the wrong place. Okay, 1, 2, 3, 4. Okay, and if I graph the line y equals x, you can see I've just created somewhat of a butterfly, if you can kind of tilt your head and look at it that way. Okay, some of the known inverse functions are things like y equals x squared and y equals square root x. Now we know that this isn't a truly an inverse function unless I have some domain restrictions. That is, if I were to solve for x, I'd also have y equals negative square root x, right, to complete it. But that wouldn't be a function. It wouldn't pass the vertical line test. Because remember, if for a function not to be broken, when I input a given value, I must consistently get out that same value. I can't get out two different values for the same input. It must pass the vertical line test. So I restrict the domain. And in Desmos, we do that by saying x is greater than or equal to 0. Okay, and now it's symmetric with the line y equals x. And there we have it. Okay, so creating that symmetry. Now let's look at a sinusoidal function here and consider what the inverse must look like. Y equals sine x. Okay, if I were to invert this, then we would the result would be, let me go ahead and screen capture this here. Okay, the result would look something like this. Okay. It would reflect across the line y equals x and turn into something like this at 8, right there, at a little before 5, right there. Okay, it would look something like this. However, we know that this would not pass the vertical line test because a vertical line touches more than once. In fact, it touches an infinite number of times if you consider how that the cyclical nature of sine repeats forever. And so we must restrict the domain in order for it to have an inverse function. Okay. All right. So let's go ahead and see if we can restrict the domain. If I restrict it to go just right here, so just right here and right here, and stop, that would work. So let's see if we can figure that out here. So sine x needs to be restricted. I'm going to restrict it to what? Where is the lowest point occur? Let me change, no, I'm not going to change the, yeah, let me change the scale, the bottom scale, to multiples of pi here. So I'm just going to put pi over 2. Okay, so you'll notice that a peak occurs at pi over 2 and the lowest peak occurs at negative pi over 2. So let's go from negative pi over 2, negative pi over 2 to x to pi over 2. And now we've restricted the domain from negative pi over 2 over pi over 2. And let's take a look at what inverse sine looks like. Now there's two ways to write inverse sine. You can say arc sine, A-R-C-S-I-N, okay? Or you can use the keyboard icon here to bring up inverse sine. So functions, inverse sine, it says sine little negative 1. This is the more common notation, okay? But I like arc sine because I can type it. Don't have to go to the keyboard. Okay, and there's that symmetry we expected, y equals x. There's the diagonal line. Okay, zoom in a little bit on that. Okay, and so we can see that works, but we had to restrict the domain so that when we flipped it, it fit. Okay, all right. So now consider cosine x. Okay, cosine x. How would I have to restrict the domain so that it passes the vertical line test? And essentially what we're looking for is restricting the domain so that it passes the horizontal line test. And the answer here is this. If I restrict the domain to be from 0 to pi, okay, that's invertible. It passes the horizontal line test, and we can check and see arc cosine of x. There it is, right? And so note that the domain and range are restricted. So the domain of arc cosine or inverse cosine is negative 1 to 1, because that's the range of cosine. And the range of arc cosine is from 0 to pi, okay? All right, so let's try another one here. Let's try tangent. Tangent of x. Now, if I'm going to pass the horizontal line test here, basically what I need to do is restrict myself to be between the values negative pi over 2 and pi over 2. So let's go. So from pi over 2, exclusive, and, or whoops, that should have been negative pi over 2. Negative pi over 2 to pi over 2. Okay, there we go. And if I graph arctan, there it is. And there's our symmetry. Notice the domain and range are switched. The domain of tangent Domain of tangent is everything but negative pi, or pi over 2 plus multiples of pi. Okay, and here the domain has to be artificially restricted to be between negative pi over 2 and pi over 2. So the range of the arctangent function is from negative pi over 2 to, or sorry, the range is from negative pi over 2 to pi over 2. The domain is all real numbers because the range of the original function is all real numbers. So domain and range are switched. Okay, so hopefully you get the idea, and we'll explore some more detail in the lesson. Oh, actually, finding the inverse trig functions of values. We need to do a few of those because that was included as one of the objectives. So here we go. Let's say we want to find the arc, and let me use the official notation, arc cosine of root 3 over 2. Okay, and give that value here. Now the arc cosine is restricted to be between 0 and pi. Between 0 and pi. Okay, because that's the restriction, and it's going to give you a value that's in that range. So I'm just going to sketch here. Root 3 over 2 corresponds with the height of a 30, 60, 90, where this is 1/2. And actually cosine is the width. Cosine is the width. Cosine is the width. So it would correspond like this, root 3 over 2. So that happens at pi over 6. So arc cosine of root 3 over 2 is pi over 6. The output of an inverse trig function is an angle. Okay, and that's important to remember. The output of the inverse trig function is an angle. Now that's not the only possible solution. There's also one down here. Okay, so this would be negative pi over 6, right? Or any multiple of 2 pi. So pi over 6 is one solution, plus any multiple of 2 pi, going all the way around. And it's also negative pi over 6 plus any multiple of 2 pi. There's infinite solutions to the equation that says arc cosine, or cosine of what angle is root 3 over 2. Okay. All right. So let's I'm going to leave it at that. I'm going to let you explore it some more in the lesson.